Now we're going to be given a square matrix, and we have to check whether it's magic. Magic means that all its row and column sums and the diagonal and anti-diagonal sums are the same. I've predefined a collection of matrices. The first one is trivially magic. There's only one number, so whichever way we sum it, we get the same number. Second one, we can check that it's magic. 4 plus 9 plus 2 is 15. 3 plus 5 plus 7 is 15. Even the diagonal, 4, 5, 6 is 15, and so on. The third one is easy to see. It's not magic. Plus 1 plus 2 is 3, but 3 plus 4 is not 3, so that one's out. And for the same reason, we can see the last one. We keep having increasing sums, both vertically and horizontally, so can't be magic either. So the first two are valid magic ones, and the second two are not. Let's apply a lambda on each one of these. We refer to the argument as omega. And instead of trying to do all the summing, we'll stack together everything we need to sum and do all the summing in one go. So here's the argument concatenated with its diagonal. How do we find the diagonal? Well, if we traverse the array and in order, but every time we go to the right, we'll also go one step down, then we find the diagonal. Effectively, if we map both axes of this matrix to a single axis so that we force walking along both axes at the same time, then we get the diagonal. And therefore, we can do this with a transpose. The generalized dyadic transpose maps axes to different locations. And if we map both axes to the first one, then we get the diagonal. So here we have the 4, 5, 6. It's been concatenated on the right. Next up, we want to do the summation of the rows. But since we're going to sum vertically, then we just need to transpose the argument so that when we are going to sum here 4, 9, 2, that actually corresponds to the original row. And finally, we want the anti-diagonal, which we can get by flipping the matrix horizontally and then taking diagonal. So we can flip it horizontally using the reverse function. So we can see that we got 294 instead of 492, and then we take the diagonal just like before. So this gives us all the columns that we need to sum. So we do a plus, insert it vertically, and the only thing that remains is to check whether all the elements are the same. So we can find the unique elements and then count them, and then check if that's equal to 1. So this is a very straightforward translation of the problem statement to APL. But there's some duplication of code, we could say. Something seems very redundant. We're taking the diagonal here, and we're taking the diagonal over here, and flipping things around. And there's actually a way to compress this a bit, which is rather neat. So let's try that. Let's start off by combining the transpose and the flipped horizontally version of the array. Because if we think about it, this reversal here allows us to take the diagonal. If we do a transpose, then it doesn't matter for the diagonal. The diagonal stays the same. So if on each of these two we take the diagonal, that gives us the two diagonals. And if on each of these two we take the sum, then if we mirror it horizontally, then the vertical sums are just in a different order, but it's still the same vertical sums. And the vertical sums of the transpose, that gives us the horizontal sums. So all we need to do is do all the combinations of transposing, of taking the diagonal and taking the vertical sums with the combined with the transposing and the mirroring in order to get all the 4 different combinations that we want. So we're going to combine these, and we're going to take the union of them, because we need to get that final set of how many different sums are there. We need to be careful not to have any duplicates, because they would persist in the union. But before we take the union, of course, we have to actually find the sums. So we pre-process the argument to the union with a little function, an inner function. And that function is going to be taking the diagonal, and we're concatenating that to the array itself. And once we've got that, that means we've got one more column, which consists of the diagonal. And then we can do the vertical sum and take the unique of that. It's important that we both take the unique here and take the union over here, because if we didn't take the unique and there were multiple on the left, multiple sums, they would persist to the end. But they could be all the same, even though they're multiple, right? Because if our array is larger than just a 1 by 1, there will be multiple sums. Actually, even if there wasn't, because we have both the diagonal and the array itself, so we always have two. But this will make sure that in the case where it is magic, in this halfway respect, we only get a single element. And then we get, if it's magic, we get a single element from the left and a single element from the right, and then the union of them will either be a single element or not if they don't match. In case there are any other elements than any other sums, then it doesn't matter where they appear. We'll always have something that has length more than 1, because the union will not be able to take away any duplicates from here. So this gives us all the different sums, and then remains the thing that we did before of 1 equal to the count of that. But since we're doing things tacit here, we still want the dyadic, the 2-argument form of equality, but we want to pre-process the right argument with the counting, with the tally. So this is a very neat compressed solution without any duplication going on. Thank you for watching.